Good morning. Today, I'd like to talk about the Cauchy-Riemann equations again, except from a different point of view. In a previous video, we convinced ourselves that if a function f of a complex variable is differentiable, then its real and imaginary parts have to obey the Cauchy-Riemann equations, which I'm going to abbreviate as CR here. What about the converse? If you had a function whose real and imaginary parts obey the Cauchy-Riemann equations, is that good enough to guarantee that the function is differentiable? This video will settle that question, and since the calculations are kind of involved, I'm just going to talk my way through them. To start with, though, I want to drop back and think about our first sort of bad example. Let's think of having a function z conjugate. The function values are x plus I times negative y. If you didn't know any better, you'd think this. You would think, well, x is a differentiable function, y is a differentiable function, x plus a constant times y should be a differentiable function, right?
Right? Wrong.
But when you apply the Cauchy-Riemann equations to this, you find out that they're not satisfied. So in point of fact, z conjugate is not differentiable. The problem is we're using the word differentiable to mean two completely different things here. In ordinary multivariable calculus, the type that you do in third semester calculus courses, you say that a function of two real variables is differentiable if you can do this: if the change in the function value can be expressed as the partial of f with respect to x at the point you're interested in times delta x, plus partial of f with respect to y at the point of interest times delta y, plus epsilon 1 delta x plus epsilon 2 delta y, where the epsilon 1 and epsilon 2 both go to 0, as delta x and delta y both go to 0. There is no idea of taking the difference in function value, dividing by the change in position, and taking the limit. But when we're doing complex numbers, we do know how to divide by a complex value. There will be a notion of dividing through by how much the input changed and taking the limit of that as that change tends to 0. So let's suppose that I have a function f of z. I can write it as u of x and y plus I v of x and y, where u and v are ordinary real multivariable functions. xy represents the complex number x plus iy. If we assume that the first-order partial derivatives of u and v are continuous, we know from third semester calculus that the u and v functions are differentiable in the sense that you used back in multivariable calculus. That is to say, the difference in the u value equals partial of u with respect to x at the point of interest, delta x, plus partial of u with respect to y at the point of interest times delta y, plus epsilon 1 delta x plus epsilon 2 delta y, and a similar statement for the v function. The epsilon 1, epsilon 2, epsilon 3, and epsilon 4 tend to 0, as delta x and delta y tend to 0. So let's think about a function, f of z, u plus iv. I want to think about the difference in function value, which for convenience I'll call delta w. The point of interest that I'm interested in is the complex number a plus bi. So in the u plus iv way of thinking about this, the x will be a and the y will be b. If I literally write down u plus iv evaluated at a plus delta x, b plus delta y, or if I wanted to think of it that way, z plus delta z, then subtract away u plus iv evaluated at ab. This is literally the difference in function values between the 2 points, between the two complex numbers. By doing ordinary algebra, I'll group the u terms together and the v terms. We know something about those quantities inside the square brackets, though, because u and v are differentiable in the ordinary sense of the word. In a little while, I'm going to take the change in function value, divide it by delta z, and then take the limit as delta z approaches 0 plus 0I. Shortly, I'm going to divide through by delta z and take the limit as delta z goes to 0. That number, that one, and that one are constants. They are various partial derivatives evaluated at ab. The delta x and the delta y's go to 0. It's a little unclear to me what's going to happen to that term, that one, and that one. So I want to investigate this. Let's think about epsilon 1 delta x. Think of dividing through by delta z. Can I identify what happens to this quantity? Absolute value epsilon 1 delta x over delta z is absolute value of epsilon 1, absolute value of delta x, and the length, the modulus of delta z, is square root delta x squared plus delta y squared. In this fraction, the number in the denominator is at least as big as the number in the numerator, so this quantity is no bigger than the absolute value of epsilon 1. That number tends to 0 as delta z tends to 0. So what this tells me is these terms that I was worrying about are, in point of fact, not anything to worry about at all, even after I divide through by delta z and take the limit. Those terms all have limits that are equal to 0, so they're not a concern. In what follows, I will either not even write those terms down or write them down in terms of some quantity capital I. Capital I is for it's safe to ignore this term. Now I'll divide through by delta z. This divided by delta z tends to 0 as delta z tends to 0. So when my writing becomes a little bit cramped, I feel free to just completely ignore that term. This quantity is what you called du back in multivariable calculus, and this is dv. In order to get something that I can work with in a little bit more convenient way, I'm going to actually do the division by delta x plus I delta y by multiplying the top and bottom by the complex conjugate of delta x plus I delta y. The bottom of the fraction becomes a real number, and upstairs I have the differential of u plus I times the differential of v times delta x minus I delta y. This is where something magic happens, but we won't see this for a minute. To keep the writing under control, I'm going to look at this quantity separately. This is the real part of the numerator in delta W divided by delta Z. If we write out what du is and then multiply it by delta x, plus write out what dv is and multiply it by delta y, after doing the algebra, we get this quantity. Now, all we're assuming about u and v at the moment is that they have continuous first-order partial derivatives. Even so, if we were Spider-Man, our spidey sense would begin tingling right about this, because that seems familiar to us somehow. More on that in a minute. Again, just to keep the algebra somewhat under control, we're going to look at this quantity by itself. After doing algebra on it, we get an expression, a very complicated looking expression, but just as with the other one, this difference shows up, and that seems very familiar to us. What if we assume, in addition to the continuous first-order partial derivative idea, that u and v obey the Cauchy-Riemann equations? One of the two Cauchy-Riemann equations is partial derivative of u with respect to y is the negative of partial of v with respect to x. If that's the case, then this term is 0. The real part of the numerator of delta w divided by delta z will then just be u sub x delta x squared plus v sub y delta y squared. But again, if u and v obey the Cauchy-Riemann equations, then v sub y is the same thing as u sub x, and the real part of the numerator simplifies to partial of u with respect to x at the point of interest times delta x squared plus delta y squared. If you think about the imaginary part in the numerator, if the Cauchy-Riemann equations are true, then that quantity is 0, leaving you with this. If the Cauchy-Riemann equations are true, the partial of u with respect to y is the negative of partial of v with respect to x, and you get a result that's very similar to the other one. It's very important to observe something here. Both the real and the imaginary parts have a factor, delta x squared plus delta y squared, and in the denominator of the fraction, delta x squared plus delta y squared appears. We have assumed that u and v have continuous partial derivatives. We have assumed that the Cauchy-Riemann equations hold. The conclusion is that delta w divided by delta z is this quantity plus a term that tends to 0 as delta z tends to 0. In the numerator, factor out delta x squared plus delta y squared and cancel it with the 1 at the bottom. Then, when you take the limit as delta z tends to 0, this is a constant, that's a constant, and that tends to 0. The limit as delta z goes to 0 of f of the point of interest plus delta z minus f at the point of interest over delta z does in fact exist if the functions u and v have continuous first-order partial derivatives, and obey the Cauchy-Riemann equations, then u plus iv is a differentiable function in the complex analysis sense of the word. Also, because of the Cauchy-Riemann equations, u sub x is the same thing as v sub y, and u sub y is the negative of v sub x. So we could write our result in this form if we felt like it. It's important to understand what's happened here. You might be thinking that at the very beginning you could have just written down u sub x plus I v sub x and said, there's your derivative. If you do that, you have found a candidate for the derivative, but you're only looking at points along a horizontal line that pass through the point of interest. We saw in our example that's insufficient. That's no good. What we've done is we've assumed that the functions have nice partial derivatives. We assumed that the Cauchy-Riemann equations are true, and the conclusion is that the limit that defines the derivative exists, and it doesn't matter in the least what manner you approach the number a plus bi. It's kind of a subtle point. So if at the onset we assume that our u and v functions have continuous first-order partial derivatives, then what we figured out the other day was, we already knew this, if f is differentiable, then the Cauchy-Riemann equations hold. What we figured out today is the converse. If the Cauchy-Riemann equations hold, then f is differentiable in the complex number sense of the word. And the reason that number 2 is true is we have a way of dividing by the complex number delta z, but we didn't have a way to divide through by delta x comma delta y. That single fact about the division is why things have worked out the way they have. Since there were so many detailed and picky little calculations to do in this discussion, I've felt as though it would be a better presentation to do it this way. Coming up soon, more calculational type material. In the meantime, I hope everybody has a good day. I'll talk to you again soon.